Hi all. Let's see the next topic of fifth unit, vector processing. So in today's lecture, we are going to discuss about an introduction to what is vector processing, what are vector operations, the instruction format of a vector processor, and matrix multiplication example. So coming to an introduction, before going into the concept of vector processing, let us understand how a normal computer is incapable of performing a task which requires the use of a more advanced computers like computers. So, if you consider a normal laptop or a desktop computer, your task is you can perform the tasks such as executing your programs and watching the videos or performing a task. But if you want to perform a huge computational task, like for example, if you want to receive the pictures from a space station, or if you want to identify the resolution from a pictures which are sent from a space station of another planet. In that case, these are huge computational tasks which are not a regular computational task, and if you want to perform these type of a task on a normal computers, they take more and more number of days or even weeks to complete the task. Here there is a list of or a class of problems which are identified which go beyond the capability of a conventional computers, which cannot be performed. We cannot say that they cannot be performed on a normal conventional computers, but they take more and more amount of time to perform the task on a conventional computers. So because of that, we require vast number of computations to be performed in these type of applications, which require the use of a vectored computer systems, which in case of a vectored computer systems, they perform huge computational tasks with the help of vector processors. Okay, so if you consider this in case of a long range weather forecasting applications like the day-to-day forecasting of your weather or petroleum explorations, and in case of your medical diagnosis and artificial intelligence and expert systems or image processing applications, all these requires to perform a huge computational task which cannot be done on a conventional computers. So they demand the use of a high processing computers, which implements the concept of vector processing. So, in many science engineering applications, the problems can be formulated in the form of vectors and matrices that lend themselves to the vector processing. So, wherever your elements or your data is processed in the form of a vectors and matrices, you implement the concept of a vector processing. And especially in the scientific problems like these, you implement the concept of vector processing. So, to achieve the required level of high performance, it is necessary to utilize the fast, reliable hardware and apply innovative procedures by implementing the concept of vector and parallel processing techniques. So, next coming to vector operations. So, many scientific problems you require to perform an arithmetic operations on a large array of numbers. So, all the information in the scientific problems is stored on an array of numbers. So, arrays which are you are going to perform addition, subtraction, multiplication, and division operations on these arrays. So, you are going to represent array in the form of a vector, where a vector is an ordered set of one-dimensional array of a data items. So, if you consider a vector of length n, it is represented as a row vector, and it is of length n, vn, v2, so on vn. So similarly, you can also have a column vector. So the elements of your problems, the data which is present in your scientific problems, it has to be represented in the form of an array, and then the arithmetic operations are going to be performed on these arrays. So this array is represented by means of a vector, one dimensional or an n dimensional arrays. So let us identify what is the difference between a conventional computer and a vector computer in terms of processing a task. Say for example, I have two arrays A and B. I want to perform an addition operation on the contents of arrays. So say I have A of 100 and B of 100. I want to perform an addition operation on these two arrays and store the result in C of I. So for that, in a simple Fortran language, we do I is equal to 1 comma 100, C of I is equal to B of I plus A of I. So when it comes to a conventional computer code which is written in a machine language, so I have to initialize a variable I to 0 first. and then and read the value of a of I and b of I. Then you need to perform a of I plus b of I and store the result in c of I. And you need to increment the variable of I, then check if I is not equal to 100, then it again goes to the label 20 and it performs the same thing. So these instructions will be executed until I is equal to 100. So this is how we perform in a conventional computer. But there are a lot of instructions that need to be executed to simply execute perform an addition operation on two arrays. So, and moreover, in a conventional computer there is no time restriction. You are not bothered about how much amount of time it takes to perform a given task. But if you consider a complex operations which has to be solved in a scientific problems, there is always a time restriction that they have the particular task has to be executed in a stipulated amount of time. So in those type of situations, we implement the concept of a vector computers or a vector processing. So this particular code which is executed using a conventional computer can be done in a simple single instruction in case of a vector computer. So in case of a vector computer, the operations that it is going to perform are a multiple, but that is implemented only with the help of only one instruction. So if you see, it is represented as c of 1 to 100 is equals to a of 1 to 100 plus b of 1 to 100. So it is going to perform an addition operation on the two arrays a and b from I is equal to 1 to 100, but it is going to perform multiple operations, but it is represented with the help of a single instruction. So that is the beauty of vector computers. Next, let us see about the instruction format of a vector computers or a vector processing. So as we know the instruction format of a normal computer, it contains opcode, operand 1, operand 2, operand 3. So here in case of a vector instruction format, the same thing, but we have for one more thing in your format, which is a vector length. So opcode specifies the operation that needs to be performed. The base address source 1 represents the first operand, source 2 represents the second operand, and destination represents the destination operand. And apart from that, we also have a vector length. So the vector length specifies the number of operations that has to be performed in the ALU as a result of executing this instruction. So how many number of operations will be performed? 100 operations. So from I is equal to 1 to 100, it performs an addition operation on these two arrays. So the vector length specifies the number of operations performed in the ALU as a result of executing this particular instruction. Okay. This is the instruction format of a vector instruction. Next, let us see an example of matrix multiplication. So first, let us understand why we are taking an example of matrix multiplication to explain the concept of vector processing. So if you consider the applications of vector processing, which are all scientific applications, in all these applications, the elements are stored or the data that is stored in a huge array of matrices. And in order to execute these applications, you need to deal with a huge number of matrices by performing different types of operations on the matrices, such as addition, subtraction, multiplication, and division. That is the reason we are talking about matrix multiplication here. So now let us see the multiplication of two n by n matrices. This is my first matrix A and the second matrix B. I'm going to perform multiplication of two matrices A into B. It gives me a resultant matrix C. And both the matrices here are a 3 by 3 matrices. Here, if you consider the output matrix here, it contains, these are said to be called as the inner products. C11, C12, C13, C21, C22, C23, C31, C32, C33. So how do I calculate the inner product of the particular matrix? C11, if you consider, I can calculate as A11 into B11 plus A12 into B21 plus A13 into B31. So this is how I calculate the inner product for the each and every inner product of the corresponding resultant matrix. Now Let us understand how do we do it using the concept of vector processing. So here we implement the concept of pipeline for calculating the inner product. So this particular vector processing contains a floating point multiplier pipeline. So it contains two pipelines, multiplier pipeline and adder pipeline. Because to calculate the inner product, we have to perform multiplication and then perform an addition. So A11 into B11, A12 into B21, A13 into B31. Multiplication has to be performed and then we have to perform an addition. So for that, our pipeline contains a multiplier pipeline and a adder pipeline. So let us consider we want to perform C is equals to A1 B1 plus A2 B2 plus A3 B3 so on AK BK. So K can be either 100 or 1000. So how that this particular instruction will be executed in the pipeline. So the source A, which gives you the input to this particular pipeline, multiplier pipeline with A1, A2 so on, where we have a source B which gives the input to this pipeline with B1, B2 so on, Bn. So at the first clock pulse, the input from the source 1 A1 and the input from source B B1 will be loaded into this particular stage of the pipeline. So each and every pipeline, multiplier and adder pipeline, it is divided into four segments. So in the first clock cycle, A1 B1 will be loaded into this particular pipeline, and in the second clock cycle, A2 B2 will be loaded here, where A1 B1 will be shifted to into this particular segment. In the third clock cycle, A3 B3 will be loaded here, A2 B2 will be loaded here, A1 B1 will come here. At the end of the fourth clock cycle, if you see, A4 B4 will be loaded here, A3 B3, A2 B2 and A1 B1. So this is the status of the pipeline at the end of fourth clock cycle. Coming to the fifth clock cycle, after fifth clock cycle, A1 B1 will be loaded into this adder pipeline, and then A2 B2, A3 B3, A4 B4 and A5 by B5 will be loaded into this particular position. So the input from this multiplier pipeline will be moved to the adder pipeline. After the eighth clock cycle, so this goes on until you get A8 B8 here. Now after ninth clock cycle, what happens is, if you see here, this output is given as an input to this particular stage back. So at the end of ninth clock cycle, whatever is output here, which is A1 B1, that is again given as an input to this adder pipeline. So in the adder pipeline, it performs an addition of A1 B1 plus, so this A5 B5 will be shifted to this place, because A2 B2 will come here, A3 B3, A4 B4. So A5 B5 will be moved from here to here and it is added with A1 B1, which is the output of this stage. So here we get A1 B1 plus A5 B5. Similarly, in the next 10th clock cycle, you get A2 B2 will come out of this. So you get A2 B2 plus A6 B6. Similarly, in the 11th clock cycle, you get A3 B3 plus A7 B7. So this continues until this entire instruction is executed in the pipeline. So this is how this particular instruction, the matrix must be performed in the vector processing pipeline. So here we are implementing the concept of dynamic pipeline. So if you consider a static pipeline, whatever input that you are giving, it will come out of the pipeline as an output. At any stage, you cannot give it as an output as an input to the any of the stages of your pipeline. In case of a conventional pipeline or a static pipeline. But in case of a dynamic pipeline, the only difference is you can give the input of your output of your pipeline as an input to any other stages of your pipeline. So here this A1, whatever is the output here, that is again given as input to this particular stage to perform an addition operation in an adder pipeline. So that is the use of a dynamic pipeline. So vector processing implements the concept of a dynamic pipelines. So this is all about vector processing. Thank you.